हां झालं सर.
Good morning, dear student. Today we discuss the second important type of inorganic reaction, that is reductive elimination. So what is this reductive elimination? Reductive elimination is the reaction is just opposite to that of oxidative addition reaction. So let us see one by one what are the characteristics of this reductive elimination reaction. First characteristic, it is just opposite to the oxidative addition reaction. Second, generally this is the last step of any catalytic process. This reductive elimination is a last step of any catalytic process. This is one of the important characteristics. So, the last step of any catalytic process, generally the saturated coordinated complex, generally saturated coordinate complex shows a reductive elimination reaction. Means there is no any vacant site at metal set. So all sites are occupied. It is considered as a saturated coordinate complex or saturated sites. For example, the octahedral complex in which all 6 sites are occupied. Therefore, the complex is called as saturated. All the sites are considered, or the complex are considered as a saturated coordinate complex. So saturated coordinate complex shows reductive elimination reaction. Next important characteristics of this reductive elimination reaction is that only 18 electron species shows a reductive elimination reaction. 18 electron species shows reductive elimination reaction. Next important characteristic is that metal atom is in high oxidation state, and it is electron deficient. So metal atom should be in high oxidation state and it should be electron deficient. Another important characteristics of this oxidative addition reaction is that we get a cis product. In reductive elimination reaction. Another important characteristic is that the coordination number, oxidation state, and electron count is decreases by 2 unit. So these important characteristics of reductive elimination reaction, that is the coordination number, oxidation state of metal atom, and the electron count of the complex, it will decreases by 2. That is 18 electron complexes is converted to 16 complexes. Coordination number 6 is converted to coordination number 4. So these are the important characteristics of reductive elimination reaction. Let us see some example of this reductive elimination reaction. Example of this reductive elimination reaction. Let us see the first example, that is iridium COCl H okay, you can write here PPS3 PPSC, COCl. So this is a 18 electron complex. 18 electron complex in which iridium is in +3 oxidation state, because this phosphine and this carbonate are neutral ligand, but this hydrogen chlorine having a certain charge. Therefore, the overall oxidation state of this iridium, it is in +3 oxidation state, or it is a +3 charge. Therefore, the oxidation state is +3. Electron count 18 electron complex, which undergo a reductive elimination reaction to give a product, that is iridium PPSC, COCl plus H. So in this case, the oxidation state of this iridium is +1. The electron count, it is a 16 electron complex, and the oxidation state of iridium is plus. So this is the example of reductive elimination reaction in which 18 electron complex is converted to 16 electron complex. Oxidation state of metal atom is decreases by 2 units. So iridium is in +3, it will reduces into +1. In this case, the ligands which are adjacent to each other, shows a reductive elimination reaction. The ligands which are trans to each other, for example, this H and this Cl, this PPS3, then H and this CO, does not show the reductive elimination reaction. Means the ligands which are cis to each other shows a reductive elimination reaction. So this is important point in reductive elimination reaction, is that only the ligands which are adjacent to each other shows reductive elimination reaction. Let us see another example of this reductive elimination reaction. That is PD, CS3, this PPS3 twice, So this is a 16 electron complex. PPS3 is a neutral ligand. It is the central atom, that is PD, it is in +2 oxidation state. It is 16 electron species, which on oxidative addition in presence of CS3 ion, it will give PD. This is a non-polar, this is a polar species. Methyl iodide is a polar species, so we get a trans product in this reaction. CS3 ion, then here PPS3, nice, and then this CS3 and this CS3. After oxidative addition, it is converted to 18 electron species. The oxidation state of palladium, in this case it is +2, in this case it is +2. On reductive elimination, it will give PD, PPS3 thrice, CS3, and this CS3, PD, PPS3, this CS3, and there is one more I is there, and we get a product, that is ethane as a product, because both these methyl group are adjacent to each other, and it will show the reductive elimination reaction. In same case, if you consider the same reactant, that is PD, with a small change, that is one of the methyl group is substituted by hydrogen, PPS3 thrice, PPS3 thrice, also undergo oxidative addition reaction, gives again reaction with methyl iodide, that is the polar species. So again we get a trans product, that is PD, CS3 ion. Here we get here PPS3 thrice. Okay, here one of the hydrogen, here we get CS3. So in this case there is a two possibility of the product. If we see this species, both these methyl groups are adjacent to each other. So one of the product is that we get ethane, CS3 plus PD, LN, PD and the remaining liquid. Another product which is obtained in this reaction is that this methyl group and this hydrogen are also cis to each other. So which ligands are cis and which ligands are considered as trans? So if we remain one point that the bond angle between the two ligands, if it is 180 degree, then they are trans to each other, and the bond angle less than 180 degree, they are considered as a cis. So one of the product is ethane. Also this methyl group and this hydrogen are also cis to each other. So we get methane as one of the product plus the remaining complex. So which is a major product? Either ethane is a major product, or either ethane is a major product, or methane is a major product. It will depends on the selectivity. Selectivity in the sense we get a transition state in which CH, if the hydrogen is a ligand, then we get a transition state in which a stable sigma bonded complex is formed, which have a lower activation energy and which results into the formation of product. But in this case, if you get this ethane, then the transition state having energy is higher than that of this CS3 and hydrogen. Therefore, the selectivity order is very important. That is, if you see, we get here methane as a major product. So why we get methane as a major product? Because in transition state, whatever the complex which is formed, that is sigma bonded complex which is formed, which have a lower activation energy as compared to this ethane molecule. Therefore, the major product is methane. So you should remember the selectivity order for the reductive elimination reaction is that first CH, then H, then CC, and then CX. X is for halogen. So the rate of reductive elimination is highest for CH elimination. Rate of reductive elimination is highest for CH elimination, then from HH elimination, then from CC, and then for CX elimination. So for CX elimination, the rate of reductive elimination is very low or very least as compared to that of CH, because the complex which is formed in transition state which have a lower activation energy. So you should keep in mind the selectivity order, or we can say that the rate of reductive elimination is highest for the CH elimination, then for HH, then for CH CX. So this is regarding to the reductive elimination. In next lecture, we will study the next important type of the reaction, that is the migratory aptitude, that is 1-1 insertion or 1-2 insertion. Thank you.